All right, let's jump right in. In the huge world of organic chemistry, there's this one simple group of atoms that's kind of the heart of everything. We're talking flavors, plastics, even the building blocks of life itself. And it all comes down to the carbonyl group. So let's pull back the curtain and uncover the chemical secrets hiding in plain sight, all thanks to this carbonyl core. So, right at the center of our story is this simple setup: a carbon atom double bonded to an oxygen atom. That's it. That's the carbonyl core. Now, depending on what else you attach to that carbon, it spins off into three super important families of compounds: aldehydes, ketones, and where we're ultimately headed, carboxylic acids. They're all cousins, you could say, all built around this one powerful little group. Okay, so if we're going to understand how these molecules actually behave, how they react, we have to get to know the personality of the carbonyl group itself. And really, it all boils down to one simple word: polarity. Now this is the key to everything. Seriously, it's all about a chemical tug of war. See, oxygen is more electronegative than carbon, which is just a fancy way of saying it's really greedy for electrons. So it's constantly pulling the shared electrons in that double bond closer to itself. What does that do? Well, it creates this permanent imbalance. The oxygen ends up with a partial negative charge, that's the little delta minus symbol, and it leaves the carbon a little electron poor with a partial positive charge, the delta plus. This separation of charge is the secret sauce for its reactivity. And this polarity isn't just some abstract idea. It has real-world consequences. Because these molecules have positive and negative ends, they kind of stick together more tightly than other molecules their size, and that means you need more energy to boil them, so higher boiling points. It also changes how they dissolve. The smaller guys like formaldehyde or acetone, they're soluble in water because that polar carbonyl group gets along just fine with polar water molecules. But as you start adding a long, greasy, nonpolar carbon chain, they become way more insoluble. So now we know what they are and a little bit about their character. But how do chemists actually make these things in a lab? Let's take a look at some of the most common ways to cook them up. One of the coolest ways to make both aldehydes and ketones is a reaction called ozonolysis. It's actually pretty elegant. You start with something called an alkene, which has a carbon-carbon double bond. When you hit it with ozone, it's like you're using a pair of molecular scissors. It just snips that double bond right in half and then caps each of the new ends with an oxygen atom. And boom, just like that, you've made two brand new carbonyl compounds. Now for aldehyde specifically, chemists have a few favorite recipes. A really common one is to start with a primary alcohol, and that just means the alcohol group is hanging off the end of a carbon chain, and then you gently oxidize it. Another way is to carefully control a reaction with something called an acyl halide. And as you can see, there are even special methods just for making those ring-shaped aromatic aldehydes. Making ketones follows a really similar logic. But instead of an alcohol at the end of a chain, you oxidize a secondary alcohol, which has its OH group stuck somewhere in the middle of the chain. You can also make them from molecules with carbon-carbon triple bonds. Those are called alkynes. And there's this classic method for aromatic ketones, the Friedel-Crafts acylation, which basically just glues a carbonyl group right onto a benzene ring. All right, we've made our molecules. Now for the fun part. Let's get into the action and see how that polar nature of the carbonyl group really dictates all of its most important reactions. And this right here shows you the fundamental move for all carbonyls. Remember that partially positive carbon atom? Well, it's basically a giant target. An electron-rich molecule, which we call a nucleophile, sees that positive charge and attacks. As that nucleophile forms a new bond, the carbon can't have 5 bonds. That's a big no-no. So the weaker of the 2 bonds in the C double bond O, we call it the pi bond, it just snaps and its electrons jump up onto the oxygen. This is nucleophilic addition, and it's the foundation for almost everything carbonyls do. Okay, but before we go any further, we have to introduce a really key player in this story: the alpha hydrogen. Now, it's not just any old hydrogen. It's specifically a hydrogen that's attached to the carbon right next door to the carbonyl carbon. That's the alpha position. And whether or not a molecule has one of these is about to become very, very important. And this is exactly why it matters so much. This slide shows this amazing fork in the road. If your aldehyde or ketone has an alpha hydrogen, a base can come along and just pluck it off. This creates a really reactive intermediate that leads to something called the aldol condensation, which is a super powerful way to make new carbon-carbon bonds. But if your aldehyde lacks an alpha hydrogen, like benzaldehyde here, it just can't do that. So instead, with a strong base, it does a completely different thing called the Cannizzaro reaction. So the key takeaway here is just incredible. The presence of one tiny hydrogen completely changes the chemical path it takes.
So, besides adding things to the carbonyl, we can also go in the other direction through reduction. This is basically the reverse of the oxidation we used to make them in the first place. With reagents like sodium borohydride, we can reduce aldehydes and ketones back down to alcohols. And if we use even stronger stuff, we can strip that oxygen off entirely, reducing the carbonyl all the way down to a simple CH2 group.
Okay, so we've seen aldehydes and ketones do a lot of the same things, right? They both undergo nucleophilic addition, they can both be reduced. This brings up a really practical question for a chemist. Let's say you've got a test tube with an unknown carbonyl compound. How in the world do you figure out which one it is?
Well, the answer, it turns out, isn't in what they have in common, but in one key reaction where they are completely different. The deciding test is oxidation.
And here it is, the definitive test. Aldehydes have a hydrogen atom attached directly to that carbonyl carbon, and that makes them super easy to oxidize. So mild oxidizing agents like Tollen's or Fehling solution, they'll react with an aldehyde and give you a really clear visual signal. Ketones, though, they've got carbon atoms on both sides, no hydrogen. This makes them really tough and resistant to oxidation. So it's simple. You add Tollen's reagent, and if a beautiful silver mirror forms on your test tube, bam, you've got an aldehyde. If nothing happens, it's a ketone. So what happens when you do oxidize that aldehyde? You create the third member of our carbonyl family, the carboxylic acids. They're kind of the final step on the oxidation train. And as this slide shows, their number one chemical trait is their acidity. They're way more acidic than their alcohol cousins, and they're really happy to give up that proton from the OH group. And, because they're their own unique family, carboxylic acids have their own special set of reactions. For instance, with a really powerful reducing agent, we can turn the clock all the way back and convert them into primary alcohols. They also do this really cool thing called the Hell-Volhard-Zelinsky reaction, which is basically a clever way for chemists to stick a halogen, like bromine, onto that all-important alpha carbon. Okay, we have covered a lot of ground: how to make them, what their properties are, how they react. Let's move into our final section and just zoom out a bit to see how all these pieces fit together and, why they matter so much. Yeah, this isn't just some abstract chemistry. These molecules are literally everywhere. Methanol, which you probably know as formaldehyde, is used in preservatives and for making resins. Propanone, or acetone, is the solvent in nail polish remover. Acetic acid, that's the main ingredient in vinegar. And benzaldehyde gives us that wonderful almond smell and is used in all sorts of perfumes. They are true industrial champions.
And this slide just sums up the entire relationship perfectly. I want you to think of it like an oxidation ladder. You start at the bottom with a primary alcohol. You take one step of oxidation, you get an aldehyde. You take a second step, you get to a carboxylic acid. And to go back down the ladder, you just use reduction. For ketones, it's a similar but shorter ladder. A secondary alcohol oxidizes to a ketone, and reduction takes you right back. It's this beautiful interconnected system.
And that really is the main idea of this whole story. Oxidation adds bonds to oxygen, moving you up the ladder to the right. Reduction removes them, pushing you back down to the left. It's really that simple and that powerful. So the next time you use vinegar in your salad or smell some almond extract or even just pick up a plastic container, just take a second, because now you know the fundamental chemistry that connects all of them, all starting from that simple, powerful, and absolutely essential carbonyl core. So what else do you think is around you that might share this hidden chemical history?